This online tutorial is about acidity and basicity constants of polyprotic acids and bases. Balanced acids and bases can be categorized into monoprotic and polyprotic acids and bases, where monoprotic acids can donate and monoprotic bases can accept only one H+, while polyprotic acids can donate and polyprotic bases can accept more than one H+. In other words, a monoprotic acid has only one ionizable hydrogen, while a polyprotic acid has more than one ionizable hydrogen. Based on the number of H+ that polyprotic acids and bases can donate or accept, we can divide them into diprotic, triprotic, tetraprotic, pentaprotic, and so on, where a diprotic acid can donate and a diprotic base can accept 2 H+, a triprotic acid can donate and a triprotic base can accept 3 H+, and so on. Polyprotic acids and bases can donate or accept their H+, step by step or all together. And we can consider stepwise and cumulative reactions and equilibrium constants for them. Let's discuss this by some examples. As our first example, let's consider carbonic acid H2CO3 in aqueous solutions, in solutions in which water is the solvent. In aqueous solutions, carbonic acid can lose 2 H+. So, in aqueous solutions, carbonic acid is a diprotic acid. The associated reactions are as follows. In the first reaction, carbonic acid loses its first H+. It is the first acid dissociation reaction of the carbonic acid. The associated equilibrium constant is the first acidity constant of carbonic acid in water. It is represented by Ka1. Ka1, the first acidity constant, the first acid dissociation constant, the first acid ionization constant of carbonic acid in aqueous solutions, in terms of equilibrium concentrations, is equal to the equilibrium concentration of hydrogen carbonate times the equilibrium concentration of hydronium over the equilibrium concentration of carbonic acid. At 25 degrees Celsius, it is equal to the 10 to the power of minus 6.35. In the second reaction, carbonic acid loses its second H+. It is the second acid dissociation reaction of carbonic acid. The associated equilibrium constant is the second acid dissociation constant or second acidity constant of carbonic acid in aqueous solutions. It is represented by Ka2. In terms of equilibrium concentrations, Ka2 is equal to the equilibrium concentration of carbonate anion times the equilibrium concentration of hydronium cation over the equilibrium concentration of hydrogen carbonate. At 25 degrees Celsius, it is equal to the 10 to the power of minus 10.33. In the last reaction, carbonic acid loses its 2H pluses. The last reaction is the sum of the first and the second acid dissociation reactions. It is the cumulative acid dissociation reaction. The associated equilibrium constant is the cumulative acidity constant of carbonic acid. It is represented by beta A. Beta A, cumulative acidity constant, cumulative acid dissociation constant, cumulative acid ionization constant of carbonic acid in aqueous solutions is, in terms of equilibrium concentrations, is equal to the equilibrium concentration of carbonate anion times the equilibrium concentration of hydronium to the power of 2 over the equilibrium concentration of carbonic acid. At 25 degrees Celsius, it is equal to the 10 to the power of minus 16.68. Since this reaction is the sum of these two reactions, this equilibrium constant is the product of these two equilibrium constants. So the cumulative acidity constant of carbonic acid is equal to the product of its first and second acidity constants. Carbonic acid in aqueous solutions is a diprotic acid. On the other hand, carbonate anion in aqueous solutions is a diprotic base, since it can accept 2 H pluses. For example, we can have the following reactions. In the first reaction, carbonate anion accepts its first H plus from water molecule. The associated equilibrium constant is the first basicity constant of carbonate anion. It is represented by Kb1. Kb1, the first basicity constant, the first base dissociation constant, the first base ionization constant of the diprotic base carbonate anion in aqueous solutions in terms of equilibrium concentrations is equal to the equilibrium concentrations of hydrogen carbonate times the equilibrium concentration of hydroxide anion over the equilibrium concentration of carbonate anion. At 25 degrees Celsius, it is equal to the 10 to the power of minus 3.67. In the second reaction, carbonate anion accepts its second H plus. It is the second base dissociation reaction of carbonate anion. The associated equilibrium constant is the second basicity constant of carbonate anion in aqueous solutions. It is represented by Kb2. In terms of equilibrium concentrations, Kb2 is equal to the equilibrium concentration of carbonic acid times the equilibrium concentration of hydroxide anion over the equilibrium concentration of hydrogen carbonate. At 25 degrees Celsius, it is equal to the 10 to the power of minus 7.65. In the last reaction, the diprotic carbonate anion accepts two H pluses. This reaction is the sum of these two reactions. It is the cumulative base dissociation reaction of carbonate anion. The associated equilibrium constant is the cumulative basicity constant of carbonate anion. It is represented by beta B. Beta B, the cumulative basicity constant, the cumulative base dissociation constant, the cumulative base ionization constant of the diprotic carbonate anion in aqueous solutions, in terms of equilibrium concentrations, it is equal to the equilibrium concentration of carbonic acid times the equilibrium concentration of hydroxide anion to the power of 2 over the equilibrium concentration of carbonate anion. It is equal to the 10 to the power of minus 11.32. Since this reaction is the sum of these two reactions, this equilibrium constant is the product of these two equilibrium constants. So, beta B here is equal to KB1 times KB2. Or the cumulative basicity constant of carbonate anion is the product of its first and second basicity constants. In addition to K's, we can here consider pK's, where pK's are the negative decimal logarithm of K's, or there are decimal cologarithms of K's. For example, pKa1 is the negative decimal logarithm of Ka1, and it will be equal to 6.35, and so on. Also here we can see that for stepwise equilibrium constants, we use K, while for cumulative equilibrium constants, we use beta. For acidity constants, we use A. For basicity constant, we use B. Cumulative equilibrium constants are product of stepwise equilibrium constants. In addition, like monoprotic conjugate acid-base pairs, here we also have conjugate acid-base pairs, and based on that, we can consider relationships between stepwise acidity and basicity constants. For diprotic carbonic acid, we can consider these conjugate acid-base pairs. H2CO3, HCO3-, where this is the conjugate acid of hydrogen carbonate, and hydrogen carbonate is the conjugate base of carbonic acid. Also, we can consider hydrogen carbonate and carbonate. For this conjugate acid-base pair, Ka of acidity constant of conjugate acid times the basicity constant Kb of the conjugate base will be equal to the autoprotolysis constant of the solvent, here Kw, equal to 10 to the power of minus 14 at 25 degrees Celsius. Based on previous relationships, we can see that acidity constant of carbonic acid is Ka1, while basicity constant of hydrogen carbonate, the equilibrium constant for the reaction in which hydrogen carbonate accepts 1H plus from solvent molecules, is Kb2. So we see that the product of Ka1 and Kb2 is equal to Kw. Here, for this conjugate acid-base pair, the acidity constant of hydrogen carbonate, the conjugate acid, times the basicity constant of conjugate base, CO3 2 minus, will be equal to Kw. Based on previous reactions, we can see that the acidity constant of hydrogen carbonate is Ka2 and the basicity constant of carbonate anion is Kb1. So we have these relationships between stepwise acidity and basicity constants. Here it is also good to mention that hydrogen carbonate in one conjugate acid-base pair acts as the Bronsted base, and in another one acts as the Bronsted acid. So it is an amphoteric species. For this amphoteric species, we can consider both acidity and basicity constants. The acidity constant of this amphoteric species is equal to Ka2, and its basicity constant is equal to Kb2. As another example, let's consider phosphoric acid, H3PO4, which can act as a triprotic acid in aqueous solutions. Phosphoric acid in aqueous solutions is a triprotic acid since it can lose 3H pluses. The associated reactions are as follows. The first reaction is the first acid dissociation reaction of phosphoric acid. The second one is the second acid dissociation reaction of phosphoric acid. The third one is the third acid dissociation reaction of phosphoric acid. These reactions are cumulative reactions, where the first one is the sum of the first and second acid dissociation reactions, and this one is the sum of all three acid dissociation reactions. The associated equilibrium constants are as follows. The first acidity constant, the second acidity constant, the third acidity constant. For this one, the cumulative acidity constant, beta A2, and the cumulative acidity constant, beta A3. We can easily write these equilibrium constants in terms of equilibrium concentrations. Since these reactions are sum of these reactions, we can say that the cumulative equilibrium constant, the cumulative acidity constant beta A2 is the product of Ka1 and Ka2. While the cumulative equilibrium constant, the cumulative acidity constant beta A3 is the product of Ka1 times Ka2 times Ka3. The values at 25 degrees Celsius are as follows. Phosphoric acid is a triprotic acid in aqueous solutions. On the other hand, phosphate anion is a triprotic base in aqueous solutions. It can accept 3H pluses in aqueous solutions. For example, we can consider the following reactions. Here, the first reaction is the first base dissociation reaction of the phosphate anion. The second one is the second base dissociation reaction of the phosphate anion. And the third one is the third base dissociation reaction of the phosphate anion in aqueous solutions. The other two reactions are cumulative reactions, as they are obtained by some of these above reactions. The associated equilibrium constants are as follows. For this one, we have Kb1, the first basicity constant, or the first base dissociation constant, or the first base ionization constant of the phosphate anion in aqueous solutions. For the second one, we have Kb2, the second basicity constant of phosphate anion. For the third one, we have Kb3. The third basicity constant of phosphate anion in aqueous solutions. These have cumulative equilibrium constant. For this one, we have beta B2, and for this one, we have beta B3. Cumulative equilibrium constants are product of stepwise equilibrium constants. Beta B2 is equal to Kb1 times Kb2. Beta B3 is equal to Kb1 times Kb2 times Kb3. At 25 degrees Celsius, values are as follows. Kb1 is equal to the 10 to the power of minus 1.68. Kb2 is equal to the 10 to the power of minus 6.79. Kb3 is equal to the 10 to the power of minus 11.84. Beta B2 is equal to the 10 to the power of minus 18.63. And beta B3 is equal to the 10 to the power of minus 20.31. Here, for this triprotic acid and base, we can consider three conjugate acid-base pairs as follows. Phosphoric acid as the conjugate acid, dihydrogen phosphate as the conjugate base. Dihydrogen phosphate as the conjugate base, hydrogen phosphate as dihydrogen phosphate as the conjugate acid, hydrogen phosphate as the conjugate base. Hydrogen phosphate as the conjugate acid, phosphate as the conjugate base. For all of them, the product of acidity constant of the conjugate acid and the basicity constant of the conjugate base will be equal to the autoprotolysis constant of solvent, here Kw. Based on this reaction, we can see that Ka1 times Kb3 is equal to Kw, Ka2 times Kb2 is equal to Kw, Ka3 times Kb1 is equal to Kw. Here also we have two amphoteric species, dihydrogen phosphate and hydrogen phosphate, where for this one Ka is equal to Ka2 and Kb is equal to Kb3. While for this amphoteric species, Ka acidity constant is equal to Ka3 and Kb is equal to Kb2. These are examples of diprotic and triprotic acids and bases, and we can extend these examples to tetraprotic, pentaprotic, and so on. But the amount of relationships will increase sharply. There is no limit for the number of H classes that chemical species can accept or donate. For example, we can construct a specific organic molecule with a specific number of carboxy groups to have the desired number of H pluses, or desired number of ionizable hydrogens. Another important point here is the fact that for these examples, carbonic and phosphoric acids, ionizable hydrogens are equivalent, are non-distinguishable. It is not important by what order we separate them. There are cases in which ionizable hydrogens are non-equivalent, are distinguishable. For example, we can consider protonated glycine. Glycine is an amino acid with the following structure. Protonated glycine, which we may represent it by HGLY+, is a diprotic acid. One ionizable hydrogen is here for the carboxy group. Another ionizable hydrogen is here for the amino acid group, for the amino group. These two ionizable hydrogens are non-equivalent. They are distinguishable. Their separation produces different products. Separation of the ionizable hydrogen of the carboxy group produces this. While separation of the ionizable hydrogen of the amino group produces this. And these chemical species are different. For such acids and bases for which we have non-equivalent ionizable hydrogens, the discussion is similar to our previous examples, to acids and bases with equivalent ionizable hydrogens, if the difference between acidic strength of those non-equivalent ionizable hydrogens is great. For example, in the case of the protonated glycine as a diprotic acid, the difference between acidic strength of these two ionizable hydrogens is great. And because of that, we can consider the following reactions. This one as the first acid dissociation of protonated glycine with the first acidity constant equal to Ka1, and this reaction. As the second acid dissociation reaction of protonated glycine, for which the equilibrium constant is equal to Ka2. the second acidity constant of protonated glycine. In fact, here we are ignoring these species, since almost all of it is converted to this one. On the other hand, for acids and bases with non-equivalent ionizable hydrogens, for which difference between acidic strength of those non-equivalent ionizable hydrogens is not great, is small, we have to treat them differently. We have to consider for them macro and macro constants. I will discuss these in my future videos. This is the end of this online tutorial. I hope you find it useful.